That was great.
Really fun time at Alfie's. That was just a really good discussion. Jim, I didn't know that you had so much modeling background or working
Yep.
with models. Can you just share with everybody what you did with the modeling? What was your role?
There were three areas they had identified as being significant CPU hogs. So what we did was converted that to run on NVIDIA GPUs, which is the number cruncher on the Summit machine at Oak Ridge, which was the machine we were working on. And at the end of the week, we were able to cut down the performance in half.
Wow.
So
Good.
that was a big deal.
So you were just a programming
Yeah.
architect junkie. It was kind of cool.
Yep. Yeah.
That's really awesome. Who is leading your team?
I can't remember his name. It wasn't the group. He was from Princeton Geophysical Fluid Dynamics Lab, NOAA's lab. And they're responsible for the actual deployment of the model on the machines, the two machines in Reston and Oak Ridge, and then the backup machine at Oak Ridge or Orlando, and keeping it well fed on a day-to-day basis. They're responsible for the operational side, whereas there was a completely different group that actually did the model, that actually wrote the code, implemented it, and then it's up to these guys to get it to run in production. So I was working with the guys that were the production team.
Now, I'm assuming that much of it runs all on different parallel processing. Were you trying to optimize that? Or?
Well, yes, because the machines that they have, they're limited, the parallelization is limited to the number of threads on the CPUs. Whereas like on the Summit machine, you've got 20, 30,000 processors out there, and you can really parallelize do loops or for loops. And that's, when you're parallelizing, that's what you go hunting for.
Oh, okay. So you weren't doing that part of it, though.
Yeah, we were. They had found the prior to the workshop. They had identified through profiling where the hotspots were, where the CPU was taking the most work, and then they separated that, extracted that out, got some test data to run it on, and then we spent the week speeding those things up, finding where the bottlenecks were, the real fine bottlenecks, so that we could parallelize, instead of running, a for loop one at a time, we could run 10,000 at a time.
Great. Wow. That's fantastic stuff. Do you have anybody from that group that maybe could give a Zoom AMS talk on the FV3?
Let me go into my notes and get the names out.
If you could find somebody who could just kind of give a broad overview of, the advantages of that kind of gridded stuff or the FV3 or what they're going to do, anything that's sort of FV3 related, I think it'd be really fun. We did have one guy do stuff with Jason Levitt.
Mm-hmm.
You know Jason?
No.
Okay, Jason's just, he's really involved in the bureaucracy of leading some of the teams. So, by the way, Jacob and Nick and James, I've been asked about our COD AMS, and I don't know if we need to send up a thing, but that would be still what we're doing. So I don't know if you guys want this as just continue from what we had last year, where you could put it on your resumes. We're not really doing much other than like maybe having a meeting on occasion. But if we can find somebody, we could probably just do a virtual meeting. But we won't do. I don't see us doing calendars. I don't see us doing anything this year.
Okay.
But we didn't spend any money last year, so I think we should be pretty good.
All right.
What do you think?
Is the Print Center even open?
Yeah, I have no idea. I mean, I would assume they have to be, but I don't know.
Yeah,
okay.
Plus that, you got the question of how do we distribute then, if we do manage to get some printed?
I think what we should just do is, we do the calendar so we can pay for the scholarships. We didn't give up any scholarships last year, so we're just running, it's not like it's costing us anything. It's not like we're spending money. Because I don't know about you, but I didn't go chasing a lot last year. I'm hoping we can go chasing this year.
Oh, Paul, that
Yeah.
article that you put up about the Carnot cycle,
Yeah.
I've got the book.
Oh, you got the book?
Yes.
It's really good, isn't it?
No, as soon as I saw the author, I know who he is. He writes the preeminent book in physical chemistry.
Are you serious?
Yeah, I'm serious. He's a physical chemist.
Oh, how much was the book? I might have to get that.
It's been on my shelf for probably 20 years.
So what's the guy's name?
Peter Atkins, Atkins. He's a Brit. And the title of the book is The Second Law.
Okay, hold on. I've got to do this. I'm going to Amazon. It's Prime Day, by the way. I just got another Alexa.
I better take a look.
What did you, Second Law?
The Second Law. It's going to be used.
The laws of thermodynamics. I got physical chemistry, Atkins molecules. Wow. I'll have to take a look at that.
Yeah, I probably used his book back in the day.
So is he the one who came up with the Atkins cycle? That's his book? That's his name?
Oh, that's a good question. It very well could be.
Wow. I don't think this is available on Amazon. Let's see.
I thought I saw it.
The Second Law. Here, wait, this is, oh yeah, it is. Paperback for 30 bucks. Energy, chaos, and form. Let me do this with you guys. Let me share the screen so you can see this book. Put you over there.
Second law, energy, chaos, and form.
Yes.
That's not a bad price.
No, 29 bucks for a paperback is not a bad thing at all. 16 ratings. I don't know who these people are, but interesting. Well, that's so fun that you know that name. So it gives even more credence to that book. It was just, is the book that I have though? Is this the book it's coming from, or is it Nature's Design?
That's the book.
That's
page
the book.
18, page 18, 19, 20. That's from that book.
Wow. Okay. Well, it's a wonderful book. So long as we're kind of here, go ahead and let's go back to where we were on page in our textbook. Let's go back to page 94.
$94, you said?
Yes.
New notebook. I'm almost out of space on this one.
So the idea on figure 3.20, because I'd rather look at the figure and talk about this and see if you guys are able to kind of focus up and listen to this. If we're starting at section or at point A, the first thing we do, like A to B is a what? Let's just define it this way. What is A to B?
Adiabat.
Well, it's a what process though? It's an adiabatic.
Ascent?
It's an adiabatic compression.
Compression.
Right? Compression.
Pressure, not height.
That piston. Now, obviously, in an engine, you're going to have the piston go up and down based on a crankshaft. But what we're saying is that we can, if you look at the mechanical universe, you can take away everything but the piston. So once you get a compression, now the pressure inside is great, right? It's way higher than on the outside. So if you just let it go, so you're basically saying, I'm going to push it, I'm going to compress it from A to B. That's what I do. And remember, who's doing the work?
At A,
When I go from A to B, who's doing the work?
We are,
Piston?
technically.
We are, right? We are doing the work. So we're pushing it down. We have to provide an external source of that ability to compress the gas. So that's how it starts. That's why the old cars started with the crank. You had to give something to get it going. And now we have electronic processes that can generate. And I don't even know how an engine works, but I know there's people who do.
Called a starter.
Okay, so you get the thing going. Then it's compressing. But then once you're at letter B with this piston, I let it go. Now, at that point, if I let it go, what would happen to it? It would just expand. And if I did nothing to it, it would expand back to the way it began. So I would compress it, doing work, the gas would expand, work would get back to the system. Now, the question that you have to ask is that a reversible cycle? And the answer is, well,
Yes.
yeah, mostly. But is it forever? Now, do you understand that in doing the work, I'm actually going to lose some of the energy? Because remember, work and energy are the same. So let me do this for you guys. Let me go in here. I'm feeling dark green today. And I'm saying that the compression is negative work from the gas. From the gas is, how do you spell gases? Perspective? I don't even know if I spell that. I don't think I usually use possessive with gas. So from the gas, you know how to say, oops. You know how to say that better? Because I don't know how to spell gases with an apostrophe.
It's actually it's just GAS apostrophe for possessive.
So this is the way I get around that. Perspective of
The gas.
gas. Now no apostrophe is needed. Okay, so it's negative work. The expansion is what? That is positive work. From the perspective of the gas. So it's the gas doing the work. Remember, the work of a gas is expansion. So if I did that piston, I put it in, it would come back out. Now, would it continue on forever?
No.
I mean, no, I would always push it in, and then we get the work back out. But the idea is, could I make it go forever?
No, because the pressure inside and outside would eventually be equal.
Well, what if I looked at it this way? And this is just, I'm playing with an idea that I want you to think about. Imagine that I am providing the work to get it started. Okay, so it is external. It's not doing it by itself. But what if the work I get from the expansion, that which is energy, can be sustained and used to do the work? In other words, I store up this energy
Oh, okay.
to do the work. So once I get it going, it could always go that way. So the question is, could it go on forever? Well, I've got to play you something. Thermodynamics, Simpsons. I've got to show you this episode of The Simpsons. So please forgive me.
Your phone is your most
I
powerful.
will never fault someone for showing a Simpsons episode.
This morning, I caught
Neither will I.
a raincoat.
I know. And this perpetual motion machine she made today is a joke. It just keeps going faster and faster.
And Bart isn't doing very well either. He needs boundaries and structure. There's something about flying a kite at night that's so unwholesome. Hello, Mother dear. Oh, that's it. We have to get them back to school.
I'm with you, Marge. Gita, get in here. In this house, we obey the laws of thermodynamics.
Okay, right? This is a wonderful thing, right? That machine just keeps, and now he said it gets faster and faster, which is really kind of the same idea. Is it possible that we could go faster and faster? So what is stopping our ability to get this cycle going forever?
Friction?
Okay, there is resistance to the stuff, which we could say is friction, or we could say if it were flowing air, what is the resistance of flowing air called?
Viscosity?
Viscosity. Okay, so we have friction and we have viscosity that's resisting this. Now, when I say I'm resisting it, what I want to do is I want to look at the first law and say, well, what does that mean? It means when I provide heat, it's going to do work, but it's also going to change the temperature. Like, this is just kind of our simple way. And we said this could be PD alpha and this could be CVdP. And we're saying that there's going to be a warming of temperature. So when I've got resistance, when there's frictional dissipation of energy, then there's got to be an increase in the temperature. So because this piston is going up and it is not a frictionless surface like anything else, what is friction doing? We are saying we are taking kinetic energy of the actual machine and transferring that into a warming. That's what we're doing. The energy is going away because we are warming something because of the dissipation of kinetic energy. And that's what's known as viscosity. Now, the idea is summarized in do you remember this guy? Does everybody here know Richardson's rhyme?
I remember talking about it.
I definitely remember hearing it before, but I can't remember.
Well, if you've got a computer, do a quick Google search of Richardson's rhyme, because I'm not going to write it out for you, but I want you to see it, or you can cut and paste it, or whatever. You find that?
Unit 1.
Which one?
Wasn't it a question in Unit 1?
Yeah, there was.
Yeah, it might have been.
That one. Okay, I know what you're talking about.
What does it say?
Oops. Big worlds have little worlds that feed on their velocity, and little worlds have lesser worlds, and so on to viscosity.
So in other words, big worlds have lesser worlds. Okay, big worlds, like let's just say an extratropical cyclone, have motion. There's kinetic energy. We are then going to take this kinetic energy of the large scale and transfer it as kinetic energy of a smaller scale. So in other words, you could, if I asked you the question, how does a thunderstorm get its kinetic energy? We could say that the large scale kinetic energy can transfer some of its energy into a smaller scale disturbance. This would be much like you kicking a soccer ball. Your leg is a much larger scale energy source, transferring that energy into kinetic energy. And this is going to go on down the scale into micro scales, etc., into ultimately what is turbulence. And we're going to see that turbulence is a dissipation of kinetic energy. When we talked about fluids, and I showed you that picture of the smoke going out and then it becomes turbulent in the wake of it all, that turbulence is a dissipation of kinetic energy. That's why when you assign a car traveling through and you put it through a smoke tunnel where you can watch the smoke going over the side, you don't want this because this is a dissipation of kinetic energy of the air, which means you're going to lose it in the car's efficiency. Now, when I dissipate kinetic energy, what is that going to do? The energy has got to go somewhere. The energy is going into warming. But this is not what we call a good warming. See, because listen to what I'm saying in this engine. So before I go on, does everybody understand what I have said so far?
Yeah, let's see. Compression is negative work, expansion is positive work.
I mean, does this make sense of what I'm trying to let you kind of big picture understand?
When you say it's not good warning, you're implying that the energy is being permanently lost as opposed to being recycled.
Correct. So imagine that I took this compression and I gave it good warming. What is good warming? On the diagram on figure 320, good warming is D to A. Because by providing an external source of heat into this gas, I am making the gas expand and it's doing work with the heat that I have provided. So
you're implying that bad warming is from B to C.
correct.
Got it.
And when I say bad warming, what I'm saying, no, not B to C, A to B. A to B is bad warming.
Got it.
Because you agree that A to B is warming, but if it were just A to B and then back down, the amount of work I get is zero, the net amount of work.
Right.
So when I look at this Q in on the first law, this is good warming. Why? Because what do I do with good warming? I can do work. Now, what would I like to have in a perfect world? What would this term be?
It would always be zero.
In a perfect world, this would be zero. Because then all the energy I provide or the work I start, whatever I do, does work. But that's not the way it works. And we also know that there is a ratio of the amount of work to the amount of temperature change that we are going to get. So now we go to, all right, let's take a look at page 95. And we start saying, well, what does the heat get used to do? And we use all these transformations that we were supposed to do. So how did that come out? Were you able to come up with equation 3.79?
No.
Okay, so now I have to open up my notebook because I cannot possibly do this again. I've done it once and I'm going to cause that to be happy. All right, so are you ready? Because I may fail at this. So are you ready to try?
Sure.
All
I
right.
was born ready, I think.
You'll regret saying that, Nick.
I said, I think.
I was born ready. Do you agree that the pressure at A times the volume at A to the gamma is equal to the pressure at B times the volume at B to the gamma? So this relationship, P times V to the gamma, is a constant in a what kind of a process?
Adiabatic.
And what is gamma?
CP over CV.
Yeah.
Right? CP over CV. So just to remind you. Now, I also know that the pressure, oops. First of all, it's the wrong color. Second of all, why is it that it all of a sudden gets large? I also know that the pressure at B times the volume at B equals the pressure at C plus the volume at C in a what kind of a process?
Isothermal.
This is an isothermal. Because PV equals a constant, nRT, and the same gas, same temperature, everybody's happy. So we continue with that relationship of the other points as well. All right, so what do we do here? Okay, so my notes are somewhat messy. It says, see the next page for the proof. So what I'm going to do, all right, if I divide both sides through by this, that goes to 1. Do you agree?
Mm-hmm.
Yep, makes sense.
Which also means PD VD equals PA VA. Because that's the other isothermal idea.
Okay.
So 1 equals 1.
Okay.
So we know that this is a true statement. Now I'm going to cross multiply in here and then divide. So I'm going to reorder. I'm going to bring the D's on the bottom and the B's up on top. So what I get, and I don't know what, I guess that's the color I like. BC times, and all I'm doing is I'm kind of rearranging the terms with the velocity, the volume first. PD equals what? VB PB all over PA VA.
Okay.
Okay, so all I've done is kind of reordered terms. Now, why do I want that? Because when I look at these expressions, I have the A's and the B's equaling each other. So
I see.
So so when I go over here and I go, all right, this is PC times VC to the gamma equals PD times VD to the gamma, which says
So
that the
for the pressure
ratio of
ratio,
PC over PD
B,
equal to VD over VC to the gamma. And that's true over on this side as well. So what does this side become? Well, PC over PD is this. So this is just VC over VD times VD over VC to the gamma,
gamma.
right? And this one is the same thing. VB over VA times VB
Whoops.
times VB over VA to the gamma.
Okay.
But that is just VC over VD to the gamma plus 1, which is VB over VA to the gamma plus 1. So, Jim, that's kind of where you got some of those gamma plus 1s. And then I can take
Whoa,
that,
whoa, 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 whoa. Where do you get? Oh,
right? Because I'm
I see. I see what you're doing.
and then I just go, and then that leads to VC over VD equals VB over VA.
Because the gamma's cancel. Got it.
And like I said, my original one had some weird multiplying, and I did it, and I'm like, I'm not sure if that's a legitimate proof. But then I found this a couple of years later, and I thought that's clean. And that's algebraically really straightforward.
Yeah.
But you don't, it's hard to see that. But I think, Jim, you were talking about this when you said, how does it come to the gamma plus 1? And it's very similar to what you did with that other. So when I look at this, I'm like, okay, that's not too bad. That proves
That's
this.
not too bad. Yeah.
You know, that proves what it is.
Yep.
So Nick, did you?
No.
What was that, Paul?
Look at 370. That's not the final equation.
No, it's not the final one, but
It's
You
just
cross
cross-multiply.
you just cross multiply to get the final solution. Okay. Never mind.
so then I can just rearrange these terms again.
Mhm.
Yeah.
So are we good with that? I mean, it's, again, to me, this is like a little bit what we would call arcane. Not many people are going to get this because they're going to look, students are going to look at equation 3.79 and go, okay, whatever. Combine those last four equations, they're just going to go, okay, fine, that's what it is. Which is not all that horrible, but I think it's good for you to see how we can prove things. So in the old movies, you know, you'd see the chalkboards with all these equations on there. Well, that's what you do. You actually solve equations. Not many people do this anymore.
Nope.
Okay,
Neither
so
does the book.
now we said, okay, well, let's look at Q1. So from this problem, they're saying, okay, Q1 is equal to the volume at B to the volume at C. So what am I doing? B to C is doing what?
Positive work.
Pot? No.
B to C.
B to C is a what?
Isothermal expansion.
Right. Isothermal expansion. So we know that we're doing, it's basically negative work. No, I'm sorry, a work in the
No,
gas.
it's positive work.
Positive work,
It's
right?
an expansion.
So B to C is going to be more work than D to A. Do you agree with that? Because the area under the curve from B to C is going to be larger than the area under the curve from D to A, which is negative work.
Mhm.
And that's going to be P dV, right? This is work. And it's isothermal, so in the first law, heat in equals work plus delta T. In something that's isothermal, this goes to 0, so heat equals work. Now, the question is, do you remember I said to you, how do you do a process isothermally? What I'm doing is I'm expanding the gas. What would expansion result in?
Increased volume.
And what does expansion result in when you're increasing the volume? What will that result in?
Less pressure.
Volume increasing.
Yeah, something else.
Temperature cools.
And I do this in my intro class. I said, when a gas expands, it what?
And heat is released.
No. That's
The temperature cools.
right. When a gas expands, it cools. This is isothermal. So do you understand I can't let it cool? So what do I need to do?
Increase the pressure.
Decrease it, right?
No. Listen, a gas expands and it cools, but this is isothermal, so I can't let it cool. So how do I stop something from cooling?
Increase the pressure.
Well, then you're doing nothing.
Okay.
How do I stop something? This is an easy question. How do I stop something from cooling?
You
You
heat
warm
it.
it up.
You heat it, right? If it's cooling because of expansion, then how do we stop that? Well, give it heat. So from B to C, I've got to be giving it heat. That is when you put it on the heat source. So B to C is on the heat source in figure 3.19. Right? Does that make sense to you?
Yeah.
Mhm.
Because it's isothermal, I know that I can, like, what does P equal? Well, P equals RT over V, right?
Mm-hmm.
So all I'm saying is in this, from VB to VC, I get R, and I'll use star, times T. Well, now what temperature is this at, according to the diagram? I'm B to C, right? So that
It's
would be T1 times dV over V. Because it's isothermal and ideal gas constant is a constant, that comes out in front, and I get R star times T times the natural log of V from VB to VC.
don't you need to include the mass as well for ideal gas? Or,
They assume n is equal to 1.
oh, okay.
Yes, right. That is that, and yes, that would be true. But here's the thing: because we're going to be setting up ratios, will it matter? Will any of these things matter when I set up a ratio?
They'll
So
just
Q
cancel.
is equal to R prime or R star times T times the natural log of VC over VB. Rule of logs to integrate this. So again, the fun thing, and I hope this is fun to James and Jacob, is that the calculus part is pretty straightforward. The calculus part is easy, right? Doing the integration of dV over V is simple. The rule of the logs you need to remember. But we've done this enough times in class, it should be sinking in a little bit better.
Yeah.
If that's the truth, wouldn't the same thing be from D to A? So an isothermal compression is negative work, right? And what I want to do is this is at T1, this is at T2. So we'd say Q2 is equal to R star T2 times the natural log of VD to VA. Are you following? I mean, I know you're writing stuff down, and sometimes when you're writing, you're not thinking.
Makes sense.
Does that make sense? I'm just doing the same thing. So if I said, well, what's the ratio of the heat in? So this Q1, we can say is heat in or the heat source, and therefore Q2 is what?
The heat sink.
All right, it's the heat out, or the heat sink. So the ratio of Q1 to Q2 is just R star T1 natural log of VC over VB all over R T2 natural log of VD over VA.
R stars cancel.
And the R stars cancel, but VC over VB is the same thing as VD over VA. So this and this cancel, and what am I left with? This is what we proved, right?
That's because of 379.
Yep. So we get that the ratio of the heat is the ratio of the temperatures.
Looks like I gotta move my zoom bar there. Hold on a second, I need to mute myself.
And that is the most important thing. That is like so important in thermodynamics, in meteorology. So, Bruce, let me ask you this, because you're kind of quiet today. Discuss what's in this box. How would you describe what is going on?
The ratio of the heat is
It'd be more, it is the ratio of, but describe a little bit more about what that heat is. Like in kind of English conceptual words, how would you say that?
yeah, Q1 is the heat that we put into it.
Okay.
And Q2 is the heat that goes out to the cold reservoir.
Okay, so
the ratio of the heat that we put into
it's the ratio of those heats that I'm doing, but that's the same thing as
that's the same thing as the ratio of the T1 is the heat that is the temperature of the gas.
right.
Yeah.
It's a temperature where, I mean, and this is kind of what I want to try to help you see. T1 is the temperature where the heat's coming in. The heat source. It's how hot is the source? When I'm running a car, what is the temperature of the heat source? Like, how would you, and that this is for anybody. What is the temperature of the heat source when I'm running a car?
The igniting of the gasoline.
The igniting of the gasoline. What do you call that, the temperature where something ignites?
Flash point?
That's the flash point.
Flash
right?
point, okay.
So the flash point. So I need to go get some more coffee. So while I'm getting coffee, could you guys look up what is the flash point of gasoline versus, like, let's say diesel?
Now, diesel is greater than 52 degrees Celsius.
Depends which diesel.
What did you guys get?
Gasoline is minus 45 C.
At 45 Fahrenheit or 43 C.
Gasoline ignites at 43 C?
Oh, wait a minute.
Yeah, I think so.
Hold on.
Yeah,
That's the flash point.
that's the flash point. And then diesel is 100 Fahrenheit or 37.8 Celsius.
Oh, okay. Well, maybe I'm not looking for flash point.
Auto ignition temperature?
Well, auto ignition temperature is interesting, right? So
Oh.
if you compress the air to 536 degrees Fahrenheit, or temperature to 536, then gasoline will burn at that temperature.
Flash point of a chemical substance is the lowest temperature where enough fluid can evaporate to form a combustible concentration of gas.
Yeah, so that's not what I'm looking at. I'm
Yeah.
looking at the actual burning point.
You want the ignition point.
Now, what I want to do then is, and I believe kerosene has an ignition temperature of 428. So in other words, and I believe that diesel, well, what did you guys, did anybody find diesel?
126 Fahrenheit, or auto ignition or flash point? Yeah, flash
Well,
point, right? Yeah.
auto ignition is probably what I'm looking for.
210 degrees Celsius for diesel.
Okay, so there we go. 536 is gasoline, and diesel ignites at a much lower temperature. Now, in a car, I'm going to have a hard time getting to 536 degrees Fahrenheit, 280 C. That's not going to happen in a car. So when I have gasoline, what do I need to add?
Spark plug.
A spark plug. So I add the spark plug, and that allows me to get that explosion there. Now, if I could get a car to get temperatures up here, ooh, that would be big, right? But what's the problem with heating a car's engine to 536 Fahrenheit? It's probably weakening the metal,
Melting the rubber.
right? So you're not able to do that in a car. So you need to get the ignition temperature at much lower rates. That's why we have a spark plug. But a diesel engine, when a truck goes, we just have to get the temperature up here to 410. And in a truck, they have what's called a glow stick, where they are actually getting it pre-warms up before the engine starts firing. Because the diesel engine doesn't need a spark. It's simply by compression. It reaches that temperature and explodes. So in a diesel engine, we're talking at about 410 Fahrenheit. So 210, let me do this. 210 Celsius, degrees Celsius plus 273, now we're looking at 483 Kelvin. So down here, you'd say in a diesel engine, that's 483. Then we need the coolant system, which is down here. Well, what is the coolant in the car? It's the radiator fluid going through the engine. And if I could make that colder, I would have a more efficient engine. So engines actually run more efficiently in the wintertime because I can drop that temperature a little bit. But what's great about what Carnot did, Sadie Carnot, is he said, look, I need an efficient engine. So now the question is, well, what is efficiency? How do I define efficiency? Efficiency is the amount of work that you can do given the amount of heat that you put in. It's a ratio of the amount of heat to the amount of work. I mean, the amount of work to the amount of heat. keeping in mind that the first, look at this, guys, the first law does this, that the heat in and the work, the heat in is going to be more because the temperature is always going to go up, right? So the engine, its efficiency is always less than 1. Well, if I look at this and I say, well, what is the work? Isn't there heat coming in and heat going out? So what this actually is, it's the heat in minus the heat out all over the heat in. So I'm saying that the work that you do is the difference in the heat in and out. The difference in the heat that you're putting in from the heat source and the heat that you're extracting into the heat sink. But simplify this fraction, what do you get?
1 minus Q out over Q in.
But we just proved that the ratio of the heats is the ratio of the temperatures. So that the efficiency, how well an engine behaves. Oh, and by the way, efficiency is often eta, that's efficiency, is equal to 1 minus T out over T in. And that becomes the basis of how we understand how well anything happens in the universe. Not just an engine, but the universe. It's the ratio of the temperatures. So look at figure 3.2.
3.2 or 320?
I'm 320.
Our constant companion.
Okay?
So isothermally, that goes to 0.
Exactly. If you keep going isothermally, you get nothing. But if I think about that blue area, and I wish I could show you easier, so I'm going to try this. I have this graph. Whatever that graph, I mean, right, this is figure, so this is A to B. It's poorly drawn on here. What I'm saying, and this is kind of the key part, is that the work done in the adiabatic compressions and expansions cancel each other out. The area underneath the curve from A to B and from C to D, if I drew this diagram correctly, will be equal. One is positive, one is negative. Does that make sense to you guys? But is the work underneath this line and this line the same? And the answer is no.
No.
So what's going to make this area, which is the total net work, it has nothing to do with the adiabatic components. It has everything to do with the isothermal components. And the isothermal components, the area inside of there, is determined by how far apart the isotherms are. The further those isotherms are apart, the more the area. Because it's the small divided by the big. Small divided by big. And the greater the difference, the smaller this value is. The smaller this value is, the more efficient the engine is. So what ultimately determines the efficiency of anything? It's the differences in the temperature of the heat source and the heat sink.
There's something incredibly, just I guess, interesting about how you do all of this just to prove something that can be summed up with 4 letters or 2 letters and 2 numbers.
Yeah, it's crazy, isn't it? But this is where the genius of Sadie Carnot was, because when they first started trying to understand how things worked, which is funny that I use the word work, how universe behaves, we were trying to come up with efficient engines, because that's what we wanted to go faster. We wanted to do stuff. And we didn't know, well, what's the limit? Well, is there a limit? And the answer is yes. The limit of an engine is not in the heats, it's in the temperatures. So, I don't know if I'm going to find this, but we did this in my severe weather class. Emmanuel hurricane engine.
Oh, I remember this.
Let's see if I can find a diagram. Nats 101, 13 lecture. What the heck? I don't want this. How do I just get that picture? Open image in new tab. That's what I want. Okay. Do you have any questions on the math over here? I mean, the math's not that bad, but understanding it physically, I think that's the key. Any questions before I erase this?
And you said for the adiabatic processes from A to B and C to D, those cancel out? Is that what you said?
Yes.
Okay.
Because, and the reason for that is they're not generating work because it's a useless cycle.
Oh, yeah, that's right, because it all just goes through temperature, right?
Right. Okay. Let's get rid of that. Let's go ahead and take away the blue screen. And what I'm saying is in here, watch what I've got. I have got air moving this way. I have got air moving from outside into the hurricane. Do you agree that the pressure is dropping? If the pressure is dropping as I move toward an area of low pressure, what is the air doing?
It's going to converge,
And
It's going to get
rise.
warmer.
no. If the pressure is dropping of the air, if I have a parcel of air in here and it's moving in toward the center of a hurricane, it's going to lower pressure. What will this parcel do?
Oh, it's going to cool.
Because isn't the air going to expand? If it's moving to lower pressure, doesn't that cause expansion?
Expansion, okay.
We always say lift a parcel because it goes to lower pressure, but this is a parcel expanding, and therefore it would cool. It would cool how?
Adiabatically.
If the air gets cold and the waters are warmer, because like in the tropics, it's warmer toward the hurricane or warmer toward the ITCZ, then as it gets colder, conductive heating is going on. So I have a flux of conduction going into the air.
So the water acts as a heat source.
So the water acts as a heat source. The heat's coming in. So this process here is not adiabatic, it's isothermal.
Oh.
Because as you want to get cooler, you're drawing in heat. it's getting heat in. Well, what kind of heat comes from warm water? Sensible and key. What other kind of heat does it get?
Oh, latent heat.
I'm assuming I'm going to pull in water vapor, right? I'm going to get water vapor coming in here. So that's giving me some latent heat. Now, it's not real yet. Where does that latent heat become real?
When it starts the ascent?
Right? In the thunderstorms, these hot towers. There's where you're actually heating the air. Now, this is not perfect, right? This is not your pure engine. You're heating the air. But the air is going up and expanding, and you're releasing heat. So what would this part of the circulation be? Technically, is it adiabatic?
Adiabatic, okay.
I mean, that's what a Carnot cycle says. But is it adiabatic? I'm getting all the heat. So it's a pseudo-adiabatic.
Adiabatic.
And really, where did the heat come in? The heat came in down here.
Right.
It just got realized there. Now, on the top of this thing, the air is moving over here. And technically what's happening, and this is kind of the fun thing, is the air doesn't really do this. It doesn't just go straight across. What the air is actually doing is coming out and sinking. And that would be compressing the gas, which would make it warmer. But does it get warmer? Really? No, because at the same time it's trying to get warmer. How do I stop it from getting warmer if it's compressing?
You cool it.
By what?
The outflow.
I have, what's OLR stand for?
Outgoing long wave radiation.
So I've got outgoing long wave radiation coming out of here. And as a result, I'm losing heat at the same time the air is sinking. Now in here, sinking air means stable, so this is your trade inversion. But I'm losing energy. I am taking energy out. That's Q out.
Is the sinking of that air to scale of that picture?
No, this is a bad picture.
Okay.
Whoever did this slide, this is not how I would draw it. I would draw it. So rather than saying the air goes all the way here, it sinks. Then, once the air comes out of here, what is it going to do? Now it's going to sink back down. That's adiabatic again. So in essence, what do I have? And again, I say in essence. I have an adiabatic expansion and an adiabatic compression. Am I doing work with those two cycles? If air going up and down, do I do any work with that?
No.
No. But I have an isothermal section and an isothermal section. Here is heat in at warm temperatures. Here is heat out at cool temperatures or at low temperatures. The bigger the difference in the temperatures, the more efficient this cycle is. The more efficient this cycle is, the faster it moves. So what's going to be the prime determining in the efficiency of this engine?
The temperature ratio.
At the tropopause, right?
Mm-hmm.
Tropopause. not tropal raws, but whatever, divided by the temperature of the SST. It's the temperatures up here compared to the temperatures down here. Well, which one do you think has more seasonal variability? Doesn't the sea surface temperature get warmer and cooler more likely? I mean, and here's the reality. I don't know what the variability is of the stratospheric or the tropospheric temperatures. There is some variability. I don't really know that much about it. But damn it if I don't know that warm waters matter. So when I have a hurricane or I've got warm waters, that circulation is going to be much stronger. But let's do this. Let me get rid of this just for a second. And this is where I think the genius of what Kerry Emanuel did. And this is the stuff that I like to talk about. This can be 30 degrees latitude, and this is the equator. Therefore, what is this? What is this then, if that's true?
The ITCS?
Well, no, what do you call this cell?
Hadley cycle?
Yeah, this is the
Hadley cell, sorry.
This is the Hadley cell. Oh, damn it. This is the Hadley cell. The hell did I? Hadley cell. Okay, Hadley cell. So when would the Hadley cell be more efficient? When I've got more, what? When I've got more heat in, the Hadley cell will be stronger. So when will that happen? Well, let's think about this. Why is heat going into the atmosphere?
Warmer sea surface temperatures?
Warmer sea surface temperatures. And obviously, by analogy, it's not only that it's warmer through conduction, but warmer temperatures can have more water vapor. So I've got warmer temperatures, I have heat in when I'm drawing air in. And do you agree? Why do I draw air in? Because I'm going from some pressure at some temperature that's cooler to some temperature that's warmer at the equatorial regions. So watch this. You guys can see this, so I'm going to show you something. Let me hide this for a second. Let me go to our new text page. Let me go to climate. And I look at, let me just look over here, MJO. Do you agree? I can get rid of this. I've got warmer temperatures here than I do at 30 degrees latitude.
True statement.
Yep.
Right? So as air travels from here to there, I'm going to acquire heat. Heat is going to go into the atmosphere. And that will be the case. That is the source of energy for the Hadley cell to run. I'm drawing in heat at high temperatures. Troposphere, stratosphere, I start losing temperatures. I start losing heat to space at much cooler temperatures.
In that picture, go down a little bit with your pencil to zero lad. Are those eddies?
Yes. Well, yeah, so that's the next thing. Look at this. How much of a difference in temperature is there from here to there?
None from the looks of it.
Hardly any, none from the looks of it.
But there's a gradient there.
Well, there's warm air here, but
Yeah.
overall, I'm not going to be drawing in air. Why? Why is it so cold over here?
So there's some sort of disturbance going on.
No, what is that?
La Nina, right? Yeah.
Oh, no
Oh,
kidding.
that's over the ocean.
That's La Nina, tropical waters. Okay, so let's think about this for a second. Let's get rid of that. And now I'm going to go here, because that's just SST. What I'm going to go look at are SST anomalies. Oops. I'm going to go to SST anomalies for this region.
Oh, boy.
So
You're really-
what are we going into? I mean, it's pretty clear as day that we're getting into a what?
La Nina.
We're in a La Nina this year. That does not bode well for a nice winter. And crazy thing is what's going on up here is I've got above normal conditions. So what is the gradient doing from there to there?
It's getting pretty big.
No. Warmer to the north, anomalously warm where it's supposed to be cold, anomalously cold where it's supposed to be warm. What's the gradient doing?
Inverting?
Gradient is weakened.
Okay, so maybe this is what you need to do. Maybe I've just gotten to the point where I can do this pretty quickly and you can't. These are not temperatures. These are anomalies. So imagine that I have a board. Do you agree that this side and this side is high? If this is an anomaly, that the high part is low and the low part is high, then what's the gradient?
Gotcha.
I see.
This is supposed to be warm, but it's colder than normal. This is supposed to be cold, but it's warmer than normal. The gradient is weakened.
Why is there in the left, that left upper oval, why is there a cold area right off Japan?
Upwelling.
Okay.
These type of things here are usually because of wind systems coming over land. It upwells cold water if it's an offshore flow.
Gotcha.
So, we've got this warm blob to the north, cold to the south. So that means the gradient is weakened. Do you understand? It's in the gradient that you're drawing in heat. So will the heat be as effectively pulled into the atmosphere?
No.
In La Nina? No. That heat is a meridional circulation, which we call the Hadley cell. So what should the Hadley cell be during a La Nina?
Weaker?
It's weak.
So weak is related to the temperature gradient.
To the gradient. It's the north-south.
Right.
But now let's take a look at what's going on east-west. Colder than normal, a little bit warmer than normal. What's the gradient?
There you're going to get a big gradient.
Now we've got a bigger gradient, but that's east to west. Well, what do we call the east to west gradient? Or what's the east to west circulation called? You guys
Trade
remember?
winds?
Not the circulation in the Pacific. Jacob, you remember?
Yes.
That's the Walker cell.
Another type of
Walker cell.
Walker cell. That was what it was called.
Okay.
So what should the Walker cell be?
That's going to be strong.
That's going to be stronger. Now,
Or stronger than normal, yeah.
stronger than normal. So the Walker cell is strong. The Hadley cell is weak during La Nina. What do you think it is during an El Nino where all of this changes?
The Walker cells are weak and the Hadley are strong.
Okay, so let's take a look at what that means from an actual weather standpoint. So here's the tropics. Let's call that the equator. And this is the .30 degrees north. What are the winds like in here? What do we call them? And this is what you were saying, Jim.
The trade winds?
The winds are the trade winds, right? They're out of the northeast. Actually, let me make this a nice, neat diagram. So the winds in the tropics are considered to be northeast trade winds. But do you agree that a northeast wind is actually a north wind plus
Yeah, you got two components.
plus an east wind?
Yes.
Okay? So during this La Nina, which is going to be smaller?
South, north
Okay.
to south.
So do you agree that the winds are going to be stronger like this? They're going to be more like this.
Yeah.
So the winds are not as, I don't know how you want to say it. They're stronger easterly. You've got a zonal anomaly. You have a meridional negative anomaly. So the winds are more like that. What does that mean is going on in this area? What's there going to be less of?
Cooling.
Mm,
No.
look at the way the arrows would be. Think about southern hemisphere being the same way.
Less wind speed? No.
Let's say the winds were like this and now they're more this way. It's going to be what?
Less convergence.
Won't you have less convergence? And where is the convergence? The ITCZ. And if there's less convergence, what does that mean for thunderstorms?
Less
moisture.
thunderstorm.
I get probably get less thunderstorms, okay? So let's go here for a second. Here's, do you guys know what this is? Actually, I want to go to, let me go to the 7-day. This, oops, is showing me OLR anomalies, outgoing long wave radiation anomalies. So over here in the green, what kind of an anomaly do I have? Do you agree they're negative anomalies?
Hmm.
So the green is negative OLR anomalies. The satellite's looking at radiation coming from the ground.
Mm-hmm.
So here's your satellite. I don't know how to draw a satellite. Let's draw a radar in space. Okay, so here's your outgoing long wave radiation. There's less than normal. What does that tell you? Why would there be less radiation than normal coming out?
There's less storms.
Why would that matter? No, in fact, look, do you agree that if this is the case, this is all based on the SST?
Oh, okay.
But we already know that where there's negative OLR anomalies, the waters are warm. So what must be in the way?
Clouds. Oh.
Because now, if a thunderstorm's in the way, what's this satellite measuring? The radiation's coming from here,
Reflecting off the top of the cloud
which
tops.
is a lot colder, which means the temperatures, it's because you're at the tops of the thunderstorms, it's a lot colder, a lot less radiation coming out. So with a lot less radiation, I see negative OLRs, which means that this area here is getting a hell of a lot more thunderstorms than normal.
Is it monsoon season over there?
Well, even if it is, it's
Oh.
still more than normal.
Yeah, right.
Lots of rains. So what country is this?
Vietnam.
Vietnam.
So somebody just do a quick Google search and look up Vietnam floods. Are there any news stories about that? Or heavy rains in Vietnam? I don't know.
Flooding in central Vietnam kills 17 since last week.
Yep.
Okay. I trust me, I don't know that. I haven't heard that. All I did was look at this project and go, oh, well, that would make sense. And it makes sense. Why? Because I'm not flaring up the ITCZ. I've got better convergence from the Walker cell. The Walker cell is weakening, and that's going to result in flooding. Now, what kind of an anomaly do I have over here in the Central Pacific overall? I have positive anomalies, which means it's less thunderstorms than normal. So OLR anomalies are basically telling us about thunderstorm activity. Thunderstorm activity says rainier than normal, drier than normal. And that's why we put the colors in green and brown, because we want to look at this, not think temperatures, we want to think precipitation.
Okay, and the caption on the bottom says 81 to 2010, so that's the baseline?
That's the baseline. Yeah, that's your 30-year climatology. So if I go ahead and just loop this, whoops, or draw little dots on the arrow. I see some heavier precipitation starting to come up. Now, where was there a lot of rain a while back?
Up in India.
Yeah, right? So look at this area here. We can go ahead and stop that. And this was a couple of weeks ago. They had some serious rains, and now it looks like it's getting at least a little bit less. So again, I would look at this and say, okay, this would have been mid-September. Was there a flooding going on in India at this time? And the answer is probably yes. See, this is what I love about observational science. You start to understand why something is, and then you can make observations and you can make assessments remotely rather than having to be there, which is fantastic. Science is really good at this. All right, so let's go over here to the world where we can do the same thing. And let's go ahead and stop. Move this over here. And where do I get, where is there, this is a 1-day anomaly. So you know what, I actually want to go to the 7-day anomalies. Where's the anomaly? Well, it's over here. That's where the hurricane was. Makes sense, right? Where is it dry? How long has it been dry?
For a while.
When's the last time you saw a negative anomaly over there? I mean, you get a little bit one in Texas. And that goes back 24. I can go, if I want to, I can load a really long image, and now I get really good control of going way back. By the way, what do you see there? This is August. Look at this guy. Super dry. Probably super hot. And now we're getting in just a change in the patterns. Now, earlier this summer, there was a region over here that I thought was kind of interesting. There's a lot of rain going on around Somalia in this area. But look at California. Do you agree that this entire loop is showing positive anomalies in OLR? So that's why the drought has been extended. And what's really interesting about this whole thing is when I start thinking about it in terms of SSTs, and let's just see this thing. And yeah, aren't the eddies cool, Jim? I mean, pretty amazing stuff.
It's amazing that it really stands out at that scale.
I like
It
how
is
it kind of
cool.
like looks like you can almost like see it like billowing out from right off the coast.
And it is because remember,
It's a wave.
water is a wave.
It's just cool to see
Waves
that.
and fluids. I'm telling you, since this new satellite's gone up and we've done all this imagery, and let's face it, who else is sitting there doing loops of SST anomalies? I mean, where are you getting this data out there? And it's all here. That's why we're trying to become this one-stop shop where everything cool is here. Notice that we tend to get very warm anomalies up to the north. Not sure if that's going to be really good, but they are anomalies. And so this is one of those signs of global warming. And what we can say is we are positive anomalies. So again, this whole idea of the engine, we are going from the high latitudes to the equator, and we have on the cold side, we have positive anomalies. So the overall meridional temperature gradient is going to be less than normal. Well, a less than normal temperature gradient, according to thermal wind properties, says that our jet stream is going to be weaker than normal. And if we've got a weaker than normal jet stream, especially over here, then we're looking at poor severe weather. We're looking at systems that become closed loads, big upper level closed loads.
Now, when you say
There's
weaker,
lots
does
of
that mean in
clouds.
terms?
Oh, sorry, go on.
When you say weaker, does that mean in terms of velocity or in
Yeah.
terms of embedded waves?
Your zonal wind should be a zonal wind anomaly.
Okay.
Your west to east wind should be weaker than normal. And we're actually, if like somebody says, all right, climate change, what are the signs of climate change? I would say the two things: the warming of the polar regions and the resulting change in the jet stream. I think that's pretty obvious that there are changes from maybe 30, 40 years ago. Now, whether or not that's good or bad, I have no idea. But it's a little bit different. And who knows what the cycling of this seasonal change is, but it's kind of interesting. But man, we're going into a La Nina. So now, if I go to current ENSO, and I can sit there and go, let's look at I like the expert discussion. And we start looking at what's going on with an El Nino. Here's the El Nino region 3.4, and we see a considerable dropout since in the last year of temperatures going from an El Nino to a La Nina. And then we can say what's the 1.2 is the anomaly for that region. Anything under -1 is an El Nino, is the La Nina. So we are definitely in a La Nina. We've got sub-water temperatures we have an upwelling of colder waters. The waves are traveling This is, they're upwelling. Here's your OLR anomalies. Here's your 850 wind anomalies. Here's your 200 millibar jet stream anomalies. So lots of these things you can look at. And then when we look at a forecast, and this is what drives me crazy, is I don't get to see what the latest forecasts have been, but the overall forecast is that there is a very high probability, over 90% of a La Nina extending through the spring. Now, according to the models, which again, take it for what it's worth, it becomes a smaller likelihood of La Nina and a larger likelihood of a neutral forecast. Eventually, the model will start bringing in El Nino because the models are based on climatology. Climatology is about cycles. And so they're saying, well, we're going to have a year of strong La Nina, and then we'll go back. It'll oscillate back and forth. Not sure I buy that, but there it is. And here's your actual models. Most of them are showing, like I could just do this, they're showing that trend. But we're definitely going to be in a La Nina. So now we say, well, wait a second, what does that mean for the United States? Here's the temperature over the last several days, very dry. Here's your seasonal outlook. And they show above normal temperatures, but these guys always have above normal temperatures. And drier than normal, wetter than normal here, and equal chances. There are some things that do let's see if I can find the one that I'm looking for. They're little pictures of the United States. I wonder if I know what this is. Let me try La Nina. Hold on. Oh, La Nina. Here's something that they gave a while back. U.S. winter outlook is wetter than normal based on an average climatology. Temperatures are warmer, although we're kind of near normal, which means what for us? It means snowier than normal. So here's some composites. DJF, what's DJF stand for? What's DJF? I can't believe you forget this. James?
I know this.
F is forecast.
Oh, December.
December, January, February.
I keep thinking of all these incredibly scientific tones.
Yeah, you all suck. We're compositing those 3 months, December, because that's what's known, if you want to be correct, that's the boreal winter. What does boreal mean? You know what boreal wind is?
Northerly wind?
Mm-hmm. So whenever you say a north or boreal, you're talking about north. So this is the boreal winter, meaning this is the northern winter, December, January, and February. This is our winter season. So temperature anomalies and frequency of occurrence. Generally speaking, it's going to be slightly cooler than normal over that part of the United States. That's your composite, which means where's your jet stream going to be?
Right over Illinois.
The Walker cell tends to, the stronger Walker cell and the weaker Hadley cell. See, I want you to think about the Pacific Ocean over here. So here's the equator. Here's the Pacific Ocean. The Hadley cell, being stronger, would create a lot more thunderstorms in the central Pacific, and that would cause the jet stream to buckle up. And that oftentimes will keep the jet to the north. But without that jet stream, the jet tends to want to come more zonally across the Pacific and then cut storms into the west. So now we're going to get extensions of the jet that will go into the United States and create cooler than normal conditions for that area. Warmer than normal conditions. So this is a good year to a vacation in Florida. This is showing you the composite, meaning these are how many times do you have it above normal, the frequency, of below normal temperatures. The trend is to get this a little bit warmer. I'm not too worried about that, but I would say this seems to be a pretty strong trend. I don't know, has Joe Bastardi talked about his winter weather outlook yet? I would think we're going to be in for some interesting stuff. So let me look at one more thing. You guys mind doing weather?
Not at all.
Not at all.
Go ahead.
So let's look at the wind speed, and let's look at a sector of the Pacific, and I'll go back to last night's 0Z. So we see these big systems, strong jets, and then they weaken as they get to the central Pacific. They come out strong and then they're weakening with that gradient. But that probably will result in troughing over the west. I don't know. There's a lot of confusion in long range forecasting. And there's some people way better than I am. But what I really like is to use this page because there's so much you can get from it. So California still is dry. It's going to be dry. It's been dry for a while, but eventually I think California is going to get wetter. That would be my forecast, which makes sense because California gets into their boreal winter and you start getting precipitation. And that's what I say. And all this because of the second law. The idea of the atmosphere getting heat sources. And those heat sources vary. It is an extraordinarily complex. Do you agree that the ocean atmosphere system is extraordinarily complex? What do we say about that system?
Infinitely complex.
Well, it's strongly
Chaotic,
yeah.
highly nonlinear.
Yeah, that's the word I like. It is nonlinear. Because there's so much ocean atmosphere interactions. That is so complex. There's no way that we model this. We don't know how this all plays. It is a nonlinear system. High chaos. Okay? When I say high chaos, I'm talking about high amounts of entropy. So now we go to page 95, bottom of 95, and we talk about entropy.
1041, Paul.
Thank you. Page 96. So what is entropy? Okay, so look at top of page 96. Let's read that. Because I think everything else we should do pretty well. So now we go back to here. I'll go back to the green. And we say, all right, in passing reversibly. So remember, all of these cycles, when we talk about Carnot, we are talking about reversible. And cyclic. Cyclic means we move about and come back to the original position. The 4-stroke engine. We get back to letter A. Oops. Reversible means we can run an engine backwards. What do you call an engine running backwards?
Refrigerator.
That's a refrigerator. So what is an engine? It extracts heat from a source. It transfers heat to the sink. And in doing so, does work. That's what I like about the animation on the Mechanical Universe. They have this little heat machine, and they're just running it. They show these little graphics. Okay, so if you haven't looked at that, or even if you have, watch it again. You'll see how this works. If this runs backward, it means I'm taking heat from someplace that's cold, and I'm dumping out heat to someplace that's warm. That's a refrigerator. The engine is running backwards. So one of my favorite jokes, and I think you should understand this. So I want you to go back to yourself as a child. And children who are kids, right, get hungry. And what do kids do when they're looking for food in the refrigerator?
Sugar.
What do they do?
Looking for sugar.
No, when they're, how do kids look for food in a refrigerator? Don't they open the door and stare?
Yeah.
Oh,
Kid that doesn't just stare. No, they're not opening it for something. They look to see what's in there. And then a typical parent says what?
Shut the refrigerator door.
What are you trying to do? Because they always are sarcastic. At least my family was. What are you trying to do? Cool the whole house?
Yep.
Okay. I mean, right? You guys laugh because you know. What are you trying to do? Cool the whole house? Now that you're a student in my class, what's your smart ass answer?
What are you trying to do? Warm the whole refrigerator?
Well, no, actually not. What
You're not.
Is, no, I'm cold. I'm trying to warm up the house.
Yeah, right.
Because once I let all that air out of the refrigerator, I have to then shut the refrigerator door. The refrigerator is now warm. What does the engine have to do? It has to run harder. An engine is taking cool air out, and where is it dumping the heat to?
The room.
The house.
So by making your refrigerator run more, you're actually warming the house, because the cool air that you get is not balanced by the warm air that you put out.
Right.
The warm air is more because the refrigerator is not 100% efficient. So opening a refrigerator door is making your house warmer, not colder. And only a student well-versed in thermodynamics understands that. So I'd like you to do that. Ask somebody, if I open the refrigerator, will I make the house colder or warmer? I bet you most people will go, you're an idiot. What are you talking about?
I'll have to make sure I still do that, so I'll get plenty of use out of it, I'm sure.
So we have a little bit more to deal with, but you know, here's the thing I like about this class. I'm more concerned about teaching cool stuff to people who are interested in learning cool stuff. So if I go on tangents, I don't care. I'm happy with that. So did you learn stuff today that might have been kind of cool and different?
Yes.
Yeah.
Yeah, it's nice to see it kind of actually like applying to everything. It's a nice little thing.
I hope you did. Jacob, do you have fun? I want you to think differently when you're watching the atmosphere. I developed this page so that I will see things that I want to see, especially when I go down here to the anomalies page. And this kind of stuff is so cool, and there's so much information you can get from it. So we developed this to give you information so that you can see things like the La Nina. And there's, by the way, when I use the La Nina sector, hold on. when I go here to pages like this, I put the little box of the El Nino 3.4 region on there so that you can see that kind of stuff. And you'll see that that's a pretty sizable La Nina going on. So fun to watch that evolution. Okay, that's the end of class. I will see you guys on Thursday. Get
All
your
right.